Sometimes I have these moments where I'm going to say something, but I'm lucky I don't. Most of the time, though, I should say, and I don't say, so that's the opposite problem. And that's the difference between type 1 and type 2 errors. Okay, so we've returned here, and we've been making a lot of progress during the break. So what's happened during the break is we've discovered that what I've been saying about the chi-square is not quite right. So we're gonna go back to chi-square. And the crucial business about the chi-square is that it depends on the summation of the difference between the yeah, I'm trying to remember what was in the denominator, and then I thought maybe I should use the same notation I used before. It might be sort of cool. All right, yeah. Okay. These P's and E's have to be the frequency, how many numbers in each bin. And not the PDF, which is what I was saying, because two people came here with computing the PDF getting different values. And what I did apparently in my spreadsheet was to use those values, not the PDFs, although I told you something different. Okay, so this chi-square is really derived based on the expected numbers. And so the ambiguity that Rob pointed out, that we'll get different chi-squared if we use the PDFs and the numbers, is true. And the correct way to do it is to use the number frequencies, which apparently is what I did in my spreadsheet. Now, in previous cases, I've printed out the values of my spreadsheet and the formulas that I used in a different printout of the spreadsheet. Apparently, I did not do that at this point, so I don't have in front of me the formula. In looking at my notes yesterday, I misinterpreted what I did. Okay, so that's clear now on the chi-squared. The chi-squared is a very unusual test because it's a distribution-based test, not a fitting test. And that actually has a very different flavor and different problems. For example, the chi-square will depend on how many bins we pick. Right, all the fitting tests are completely unambiguous. If we fit a line to the data by least squares, no matter how we do it, we should get the same line. But different ones of us who have different feelings about bin widths and numbers of events in bins could do the chi-squared and get different chi-squares. So this test is different than some of the other statistical tests in that sense. Okay. So we're continuing right along to these non-parametric paired tests. And the next one has a number of different names and slightly different variations under each name, but I'll describe them all together. And it's called the signed rank test, and is also called the Will-Coxon test, and is really related to another test. It's very similar. It really uses the same statistics, although in a slightly different way, called the Mann-Whitney U-test. And we're going to discuss the paired version of this. Paired, again, means we're always comparing control and experiment for the same subjects. So this is a within-group design. Okay. This test is used, probably one of the most used tests in psychology, actually. It's very widely used. And it's used much more than the t-tests and the z-tests. And if you look in a lot of psychological literature and articles, this is a very commonly used test. And let me derive how this test is done. And in my notes, we have one of these magic transformations that you saw on Wednesday happen to notation late at night. When you're not looking at me, you do it right during the day and you put it away, and in the morning it's different. So in this test, the way I'm going to describe it is if we have two sets of data, xi and yi, These I've been calling so far control and experiment, but we'll now call them x and y. And what we're going to look at in this test, and I'll describe it symbolically first and then give an example. We're going to look at the statistic z, which is not the z from before, which is the difference between y and x. And then we're going to look at the absolute value of that z. And then we're going to rank order them. And we're going to keep track of the sign by another variable. So if one is greater than the other, we'll set that variable equal to 1. And if one is less than the other, we'll set that variable equal to 0. And then the statistic will be, which we'll call t plus, will be equal to the sum over all possibilities of the rank times the value of this dummy variable. And this should make no sense whatsoever. We'll see in the table as we develop this what this looks like. This is not my favorite non-parametric test, but it's close to it. We're coming to my favorite non-parametric test very soon, and it's really related to this one.
This looks more like it's testing to see if the experimental values are greater than the control value.
Or different than, either greater or less than, yeah.
But if it's less than 0, you're multiplying by 0, you're going to get 0 for that.
We'll see that we can do all of these in a mirror symmetric way. So we can define this just in the reverse way and do the test, and then we're dealing with the other tail. So, so it's symmetric. And we'll see that that's symmetric. So this is sort of nonsense, so let me give you the example. And here I have to copy the numbers correctly because I'm going to analyze, probably today, but again, depending on how fast I talk, we're going to analyze the same data set by about 10 different tests. And I'm going to show you all the p-values that come out of all these different tests from this one data set. So it's going to be an interesting data set. And I've chosen it to have particular characteristics because that's what I wanted to do. And I wanted to illustrate some points. So the values of this data set are 1.1 for x, 2.1 for y, 3.1 for x, 3.5 for y, 4.8 and 5.1, 1.2, 1.0, 1.8, 2.4, and 1.9, 2.0. Okay, now this is the sort of data set that particularly is not good to analyze by Gaussian statistics. And again, I'll repeat why. Only in one case is the y smaller than x. In all other cases, the y is greater than x. But there's a huge variability in the y. So if I were to take the mean value here and the mean value there and compare it, there wouldn't be much difference. And yet each one of these, with one exception, is bigger than the other one. So there's something going on here, but it gets buried when we do the Gaussian statistics. Okay, and we're going to see this, the non-parametric statistics specifically show this up. And this is true for a lot of data that I handle. Although I've made up a more extreme case than usual here, this is very typical of a lot of data that we see an effect in the experiment each time, but there's a lot of variability from subject to subject. So this is not so uncommon in real data that I have. Now let's see how we do the analysis. So let me define Zi, which is yi minus xi. And so the Zi's here would be 1.0, 0.4, 0.3, minus 0.2, got it right that time, 0.6, and 0.1. Now we'll do the absolute value of z. So this is now 1, 0.4, 0.3, 0.2, 0.6, 0.1. Now I'll do the rank of the absolute values of z. So let's call the smallest one 1 and the largest one 6. So the rank here is, this is the smallest one, 1. Next smallest one is here, 2, 3, 4, 5, 6. So you understand what the rank here means. And now we have this variable phi I, and This variable is 1 if z is positive. So this is 1, 1, 1, 0, 1, 1. And now here what we do in this column, this last column, is the rank times phi. So I've run out of space at the top here. Maybe we can cheat a little bit here. So this last column is going to be the rank times phi. So it's going to be Ri times phi. It's a shame you can't do this for blackboards as well. I guess you can if you have a little piece of slate that you move around. But OK, so now if I multiply these together, 6 times 1 is 6, 4, 3, 0, 5, 1. And I take the sum of all these, I get 19 if I did this correctly. 10, 13, 18, 19. OK. Now, one of the things I might try here is I could do a sign test on this that I did before, a binomial test. So I have 1, 2, 3, 4, 5, 6 things. One out of the 6 times I got a hit. So the probability from the sign test that we get 1 out of 6 is the probability we get 0 plus the probability we get 1, which is 1 plus 6 times 2 to the minus 6, which is 0.11. So if I was doing a sign test, the probability would be 0.11 that x and y have the same measure of central tendency. So I do that as an aside. Now, the way we handle a rank sum test.
How did you rank it?
Okay. Rank is the size of these things. So this is the smallest to the largest. This is the smallest, the next smallest, the next smallest, the smallest, the next largest, the next largest, the next largest, the next one, and the next one. Okay? Are there any other questions on how I generated this table? Okay. So the statistic I get is called T plus. And now I reject the null hypothesis. That is, null hypothesis is that x is the same as y. If T plus is less than or equal to the total number n times n minus 1 over 2 minus this little t, which is a function of p and n. And t at the 0.047 level for n equals 6, because I have 6 numbers, turns out to be 19. So the question is t plus less than 6 times 7 divided by 2 minus 19, which is 2? And I'm in trouble here because I have t plus is like 19. So I've in essence computed it just the wrong way. I've got to go back and deal with the table by making the fees just the opposite way. Well, I've made the fees 0 for this one. I should make them all 0 for the other ones and 1 for this one. See, exactly the problem that Rob was asking about. I'm on the other tail of the distribution. Okay, because I could have picked either variable, and I was unlucky. So if I go back and redo this table just the other way, I'll get for the ranks, I'll get t plus equals 2. You can see that here because if this number is 1, I get a 2 here, and all the other things are 0. So t plus is 2. This is confusing, but I'm just showing you that this is what happened because I really did it. And sometimes half of the time you're on the wrong side. Okay, so now I have t plus is 2. And now we find that t plus is less than or equal to 2, which is what we've got at the probability level of 0.047. So the p-value now is 0.047 is the statistical significance. So the answer is that the p-value was less than 0.047. Now, in computing this t statistic, you look this up in tables, and you get different values of t for different p-values. And you can see they're not distributed in some even way. They come in this odd way that I have a program in BASIC that calculates. This is actually the program that if he gets up to doing all the pieces of it that Corey is in the process of rewriting to C. But he hasn't started on many of the pieces, but he'll be doing lots of different pieces of this. So we have a table. These values all come from a table, which is in the back of the book. So you basically look up a certain probability level. That gives you a t. You compare it to the t from the data, and then you get the p-value. Or you get whether it's significant at that p-value. Again, because it's easier to compute the tables, you do this test backwards in the way we've done the other tests before. But I have a program that actually does the test one or the other way and pops out the p-value. And as I said, it's a little hard to compute because it's done in an iterative form. There's not a closed form to develop the value. Now, there's an asymptotic form for this statistic, and the asymptotic form is that z equals t plus the statistic minus n times n plus 1 over 4 divided by the square root of n times n plus 1 times 2n plus 1 divided by 24. So this is the z statistic that corresponds to that t statistic probability. So this is the asymptotic form. And as I said, I found at least one program on the Macintosh that used this form instead of calculating it correctly as I did. Okay, so you at least have a vague idea how this test is done, even though it's a little odd. Are there any questions on this? There could be questions on this, so I'll hesitate for a moment if there are any questions on this. You understand why it gets flipped over, why we had to do this twice?
But how do you know? Yeah.
Well, in this case, we do it, and if you get an answer that looks like it's skewed at the far end, then you should do it the other way. It's very clear. There's actually a dividing line. If there's no statistical significance, the t plus is a certain value, which is kind of in the middle of everything. And if it's way off on one side, then you know you did it the wrong way. Okay, and formally, in terms of the test, you can see that. Because you're accumulating, you're looking for the tail, and there's too many of one side. So you can see that. Okay, so let me now do my favorite test. So this is my favorite test. My favorite test. Okay, as Teich would do it. This is exactly similar to one we just had, only it's unpaired. So this is an unpaired rank sum Wilcoxon.
So do we have to write LFT?
That's more like Teich. Okay. This is an unpaired rank sum Wilcoxon. And it is related, as I said, it's very closely related to the Mann-Whitney U test. What we do here is we have a set of numbers, and this is, I think, the example from in the book, the Hollander and Wolf book. Let's say we have a bunch of measurements that are not paired from x, which are 0.8, 0.83, 1.89, 1.04, 1.45, 1.38, 1.91, 1.64, 0.73, 1.46. And let's say the y measurements are 1.15, 0.88, 0.9, 0.74, 1.21. Now, this is a very typical case experimentally where the number of values that we're comparing are unequal to each other. And we had this in the t-test. And what we'd like to know is, the null hypothesis is, do x and y have the same measure of central tendency? So they have the same central tendency. That's what we're trying to ask. And this is the test that handles that. So what we do in this test, and maybe I'll show my handwritten notes instead of rewriting them. No, maybe I'll rewrite them. Is we rank order all the data. So I'm going to call this x and y, And if I place them in order, it's 0.73, then the next one is 0.74, next one is 0.8, 0.83, 0.88, 0.90, 104, 115, 121, 138, 145, 146, 164, 189, 191. I'll pan back a little bit. So I've ordered them, and I've kept track of which is X and which is Y. And now I'll write down the ranks, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15.
But you have much more values for each.
Right. It's okay. It's no problem. It's not a paired test.
Oh.
So sometimes we do this, like we do 3 measurements on the control, and we do, let me say more typically, we do 10 measurements on the control, and we do 8 measurements with acetylcholine because we screwed up 2 of the measurements. So that's typical. That's not such an unusual case. This will work too if they're equal and unpaired, but we're going to stick with equal and unpaired. Okay. So now what I do is I look just at the ranks of one of them. In this case, we're going to look at the, and I can do it both ways. Again, so if I just take the sums of the ranks of, let's say, the Y values, then that's rank 2 here. It's rank 5 and 6 here, rank 8 and 9 here. And so if I take the sums of those ranks, it's 2, 7, 13, 21, 30. Okay? So again, what I've done is only for one of them, and I can do the same thing for the X. So I take the sums of the ranks. This is very similar to the previous test. So you got what the procedure is? And I could do that for either one. That's why it's called the rank sum test. And this statistic is called W. And if W is greater than some W, which depends on the probability level, the number of X and the number of Y values, then we reject the null hypothesis. Or we can reject it on the other tail if W is less than ny times nx plus ny plus 1 minus the W up here. So these are the 2 tails. And it turns out that looking at table A.5 in Hollander and Wolf, this W for at 0.082 at 10 and 5 corresponds to 52, and the W at the other tail at 5 times 10 plus 5 plus 1 minus 52 equals 28. So this means since R30 is not less than 28, no, that means we cannot reject the null hypothesis. So there's no difference. So in this case, there's no difference between X and Y, between the measures of central tendency of X and Y. Now my program, when you automatically put in this data, what it has, it reads 2 files. It reads an ASCII file of the X data, an ASCII file of the N data, and it crunches. It crunches for some time, actually. It takes a couple minutes, about a minute, because it's got to do this entire iterative thing. It builds up a large N by N table, starting at putting in boundary conditions and iterating a system of equations. It takes a few minutes, actually, a few moments, about a minute. And at the end, on my program, the number 0.127 pops out. And so this is not statistically significant. So therefore, we know there's no difference between the means. If you actually are interested in actually running any of these tests, you should look at Hollander and Wolf and or try to get the program from me and translate it into BASIC and give me back the copy in C. So I can use it. things have gotten desperate. I needed to test something in relationship to this argument with the referee, and I copied the basic program, bought it at home, where I have a Macintosh that's one of which is running on System 7 and another which is running on like System 4. And it runs on one of those machines. But things are getting more and more desperate. The disks that those machines read, one of those machines read, the machines in the lab can't read anymore. So it's getting worse and worse. Okay, well, as usual for all of these, there's an asymptotic form. And I'll write down what the asymptotic form is. Z equals W minus ny times nx plus ny plus 1 over 2 divided by the square root of nx times ny times nx plus ny plus 1 divided by 12. These formulas come out of combination. I can tell you, in this case I don't know, where these formulas come from. You think about it, let's say we order a whole bunch of things. We're trying to get the probability of all different orderings of these. And then we ask how far down the list will we find all the red ones. So this is a combinatorial problem. And you can think that this is going to be related if there are enough of these to a Gaussian distribution that will depend on some factors of the probability of a half raised to some power. And it's multiplying the halves and other things together that are going to lead to the funny numbers here. So it's actually an interesting problem. And the way you determine the probabilities is you say if there was only 1 in this position, we could then calculate the probability that it would be in the next position, because it's just interchanging these two. And so you build up an iterative table iterating on 2 variables. Given this one, you can compute that one. And then given this one, you can compute if there were 2 red ones. So you keep building up iteratively each time this table to get to the condition you're in, and that gives you how many possibilities there are. And that's how it's done. But I don't have the derivation written down anymore. I just have the program, so it's not so easy actually to do this. But this is the flavor of how the derivation is done. Okay, and again, I once had a program that used these asymptotic forms instead of the real things. Again, now we're faced with the problem. If we have these 2 sets of numbers, we can tell whether x and y have the same central tendency or not. But we'd like to get an estimate of how different they are, a quantitative estimate. And we'll use the same estimator that we used before. Now, Hollander and Wolf uses different names for this. I'll use one of the names they call this, which is the Hodgson-Lehmann estimator. And I mentioned this before in terms of least squares. And what this estimator is that the difference Zi, which is the difference between xi and yi, is equal to the median of these differences Zi. So if we want to tell, if we found that they were statistically significantly different, or even if we didn't, if we wanted to get an estimate of what the differences are, then a good way to do that is the median of these differences. Okay, now, I have a comment here, which if I can read, I can explain to you. And that is, I've discussed 3 tests. Well, a couple of different tests. The parametric tests, the sign test, which I've also called the binomial test, and the rank sum test. And I would rate them in the following order. I think that the rank sum test is better than the sign test which is better than parametric tests. And let me see if I can say why. The parametric tests are comparing these means, and as I said before, if we have a paired thing, so this is for paired stuff. If we have something that's paired, we're losing information in the means because we're combining across subjects. On the other hand, the sign test doesn't do this, but it only says whether something is greater than or less than. It doesn't say by how much. So this is sort of too sensitive to how much. This is not sensitive enough, and this is just right to how much. Meaning it uses the ranks to get how much, but not the values, which would make it too sensitive. So that's why I think the rank sum, this is based on something called the power in type 1 and type 2 errors, and there's more information going into this ranking than it appears, I think. But this is sort of the difference. That here we're too sensitive to the values. Here we're not sensitive enough, and this is some middle compromise. And so that's why I think the rank sum is usually better than the other tests. The differences here are not large, but I've tended to favor the rank sums. Okay. Now, what I thought I would do with the rest of the time today is give you a number of different tests applied to the same data set and show you how they all look different. And the data set that we're going to choose, as I said, is this one that I've picked to have properties which are not uncommon in data, but which are bad for parametric tests. And it's the data set that I said I would use, which is this one that we had before with these values between x and y. So again, I'm going to point out how I did this so you understand why this is a bad example for parametric test, is that only 1 out of 1, 2, 3, 4, 5, 6 times is y greater than x. And in all the other times, y is smaller than x, right? So far, signs are gone. If I start losing words next, we'll see what happens. Y is less than x. So 5 out of the 6 times y is greater. But when it's greater, it's only a little bit greater. And there's tremendous variation in both x and y. And as I said, this is very typical in psychological. In fact, it's very typical in a lot of paired experimental data. So it's not so unusual. There's no hint at all that either of these have a Gaussian distribution, because there are a lot of big outliers. So this is not Gaussian. It's a small number, so even if it was Gaussian, it wouldn't look Gaussian. Okay, so this is a little bit of a bad data set for Gaussian statistics, but I picked it to illustrate how the different tests give different values. If the data was more Gaussian, the difference between these tests would be a little bit less. And I haven't done that because I'm too lazy to do too many of these things. But I've done this one on all these different tests so you can see. So let me run through the different tests for this data. First, back down here. And all of these are going to be one-tailed, because that's what I felt like. And it's just simpler. I don't have to multiply by 2. So the first test we'll do, we'll do paired tests. Now we could do unpaired tests on paired data, right? We could be that stupid. And I do that sometimes. So we're going to get to that later. But we're going to do paired tests. We're going to first of all do a non-parametric test. We're going to do the test that I described twice, which is the sign test, which I also call the binomial test. Okay. Now, what we've got basically, we've already done this test. We've gotten the fact that 1 out of 6 times 1 was smaller. So if we add the probability that it happened never plus the probability that it happened once, then we'll get the correct value. and that will work out to 1 plus 6 times 2 to the minus 6th, where the p-value will be 0.1094. Now, this is the exact value. I said that for all these tests, we can have an asymptotic formula, assuming it's Gaussian, which is silly because we know it's not Gaussian. That's why we're doing these tests in the first place. But a lot of programs use this formula, and all the books have this formula. So I could do the asymptotic statistic of the sign test. And when I do that, the asymptotic statistic z is 5 minus 6 times a half divided by 6 times a half square root. And that's equal to a z of 1.633, which is equal to a p-value of, p is greater than z, one-tailed, of 0.0512. Maybe we'll put a box around this one, a box around that. So now we haven't done so badly here, or so well, because these are the same test, and we got two different p-values. Remember, we got the p-value here because we were using this as an approximation to get this. And it's not a good approximation when n is small. Okay, and n here was 6. So this value, this asymptotic thing, this is the same test, just gave a different p-value because this was a bad way to get the p-values. Okay, so that's the first test. Now, let's look at another test. Let's look at the rank sum test. My test. Okay. Okay? So now we can do this exactly. Let's do this, the rank sum exactly. So we have the t statistic, and we've already done this, was 19, and we got a p-value of 0.0470. Now this is already kind of interesting because this rank sum test is much more statistically significant than the sign test. This is what I was just saying, that different tests have different power to pick up different statistical significance. And already we've gotten a factor of 2 in the probability over this other test. I mean, isn't that interesting? A factor of 2 in the probability, just like that.
Why did you use 90 now and not 2?
I don't know. Probably because it was the one I started with. You can flip around the tail by comparing it to the other thing. And there's no, the 2 is the same as the 19. I can use, let me say it this way. There's a simpler way to look up the data in the table. And if you pick one of the things, it's easier to do it that way. If I pick the 19, I look up the number in the table and convert it, but I'll get the same p-value from the 19 as from the 2. And it has to be that way, because there's no a priori, there's no reason for choosing one instead of the other. But the answer here, I just wrote 19 because I probably looked at the previous page and saw the 19. So, but again, I'm doing this in a slightly disorganized way. But if you want to use these tests, if you look at Hollander and Wolf, they're very clear. Or if you use the programs that someone will convert, they'll be clear. So, but it's the same p-value. Now I can do the approximate, the asymptotic form of this, and in this case, z becomes t plus minus n plus 1 over 4, this just over 4, and then over the square root n plus 1, n plus 2n plus 1. It's okay, I'm writing it very sloppy. It doesn't help to see. This is just the formula I used before, and I've actually, the answer is, if you use the formula when I wrote it before that you could read it, it was z is 1.782, and that leads to a probability value of 0.374. So again, we can see that the p-value calculated exactly differs from the p-value asymptotically, but it's not a huge difference in this case. But it's a little bit different. And as I said, I had a program that returned this one instead of that one. Okay? So now we can do a parametric test. Let's do a parametric test. Let's do a parametric test. So let's do a paired t-test. And these are paired values, so we're still, doing the right thing. And in this case, I just plugged it into a program I have at work, which works, and the t-value was minus 2.174 for 5 degrees of freedom. Remember, 6 minus 1, 5 degrees of freedom. And the p-value I get is 0.082. So what's interesting about this is that before we had p-values from my favorite test of about 0.05, and now from the t-test it's 0.08. The t-test is less good at picking up the statistical significance, which is true because it's got the problems associated with it about just the function of this data. And I don't have a z-test on this. I don't know why I don't have that. Okay, now I can do something else. Actually, just to give you a feel for it, this is actually the program that computes the p-values for the rank sum test. So it just has some things that get entered into the program. And this is the starting, initializing some of the values to doing some of the calculations. It's got these funny numbers here because it wants to approximate the probability of a Gaussian, because it's also going to print out the asymptotic form of the number as well as the exact form. And then here it starts in these loops, so it starts to iterate some things. And then it continues those loops a little bit more. And then it calculates the asymptotic form, so it calculates the z and then estimates the probability from that. And in order to find the median, it's got to do a sort to find the median. So this is a sort program, and it's doing a sort. So you can see this is a little bit longer than a one-line statement, which is why they use the asymptotic form sometimes. And I have another program here, which is in BASIC apparently, that does chi-squared, or used to do chi-squared when my computer could print out run BASIC. Okay, so okay, put these together. So now we can be stupid, not stupid, but unthinking, and do a non-paired series of tests on the same data. Remember, I tried to prove once before that if we use a non-paired series of tests, that it's almost like having half as much data, that we lose a lot of the power of the tests. So now we could do the non-parametric rank sum test. We can't do the sign test because that assumes that the data is paired. So we can't do the sign test. We have no sign test here because that assumes we're comparing 1 and 1. But we can still do that unpaired rank sum. And when I do that, when I calculate the probabilities exactly, I get 0.242. And when I do the asymptotic calculation, I get 0.212. So this is a big difference. Because last time, remember, I got 0.05. Now I got 0.2. And that's the difference in the rank sum between a paired and unpaired test. And I can also do a parametric test. So I'll do a parametric unpaired t-test. And when I calculate, I got, in this case, t equals minus 0.447 for the unpaired test. Nu equals 10. Because now it's, why is it 10? It's 12 minus 2, right? In the unpaired test, we have n1 plus n2 minus 2. So it's 6 plus 6 minus 2 is 10. And the p-value here is 0.664, where before I had a paired p-value of 0.8208. And now the unpaired value is 0.664. So that's a big difference. Okay, so far in this one data set, let's see what we have for the range of p-values. Maybe we can make a little table of this. We have p-values that run all the way from smallest one of 0.0374 all the way to 0.664 for the same data. What? No, I don't know. Well, the distribution would be whatever it is, because I picked the tests. One of the oddest, this reminds me of a story actually, one of the oddest posters I ever saw at a scientific meeting, and I still can't think whether this is, choosing my words carefully, complete nonsense or was actually interesting. And it was a poster that was authored by about 8 people, mostly residents in, I think, Minnesota somewhere. First of all, I didn't understand why it took 8 people to do this, but they went through about 100 articles in the ophthalmology literature and found out how often they use each statistical test. And this was a list of the distribution of those statistical tests. Now, that seemed like sort of a desperate move to get an abstract for a scientific meeting with 8 authors. Their argument, though, was that if you wanted to learn statistics, you should learn those tests, because that's what people are using in the literature. So I thought that was an interesting idea, actually. But you should also learn what the tests are and which are good and which are bad, not just which people are using. So in another sense, and none of the people knew anything about the statistical tests, or almost nothing, because I talked to them a little bit. And there were at least 3 co-authors in front of the poster of all the 8. I guess the other 8 were at other parts of the meeting at that moment. And I couldn't decide whether this was, as I said, a good poster or a really bad poster.
Maybe you just needed a free ride to the conference.
What?
Maybe you just needed a free ride to the conference.
Well, they were from Minnesota, and the conference was in Sarasota, Florida. So, but they took it very seriously. Okay, so we have quite a range here, right? I mean, this is everything from statistically significant to nothing. So one of the things I want you to get a sense from this is how you pick the statistical test determines a lot about the p-values you get. I know a lot about picking statistical tests. So people come to me and I say, if we want a significant result, you pick this test. Okay, because I know how to do that. Okay, now, one thing is not fair. Not fair. You can't keep trying all tests. You can't keep trying tests and pick the one you like. Because that's not fair, because if you have a set of picking from an infinite set, you'll get anything you want. So that's not fair. You have to decide in advance what you think is reasonable and what you want and what's appropriate, and then use that one. You just can't play all over the field about this, okay? So that's one of the issues that comes up here. Let me write all the numbers together so we can see how the different numbers look like. So let's first of all start here with the paired tests. And we had the non-parametric tests. And in terms of the non-parametric tests, we had the sign test. And the p-value for the sign test was 1094. And I'll place this in parentheses because this was the inaccurately calculated asymptotic value. In a way, we don't really want to deal with this one because it's not really legitimate. And then we had the rank sum. And that had a p-value of 0.74 and an error, an invalid one. This was the lowest one. And then we had, still in these pairs, we had parametric tests, and we had the t-test. And that was 0.082. So let me try to highlight what I think are the real values. Okay. And then we had these unpaired tests. So this was paired. Now we'll do the unpaired associated with these. And the unpaired tests we had were the non-parametric rank sum, which had a p-value of 242 and an inaccurate p-value from the asymptotic one of 212. And the unpaired t, so the parametric t-test, unpaired, and that was 664. Okay, and let's kind of look at these values. The first thing we learn is I've emphasized here that, okay, the unpaired tests when we have paired data are a silly thing to do. Okay, and I think this really emphasizes that all of these values are much stronger in significance than these two values. So if we really do have paired data, we should use a paired test. Okay, that is, if we have a between group design, within group design, and we're looking at how one subject fares under different treatments, then we're really much better off doing a paired design. So that's one issue. And I think we can see how strongly that affects the results of all of these tests. That's one issue here. The second test is that in general, the non-parametric test seems stronger than the parametric test. Certainly this one is stronger than that one, and this one is stronger than this one. And in general, we're better off with the non-parametric tests. You can also see here that we're better off calculating the p-values correctly and not asymptotically. And that, in general, the test which I listed as my favorite test seem to be the strongest in providing statistical significance. And that's part of the reason why I like it. And it's also simple and straightforward to use and does not assume that things are Gaussian. So let me write that down. So the lessons from this, just to repeat it, are first of all, when we really have pairs, it's really helpful to use a paired test. Second of all, that in general, the non-parametric tests usually are more powerful. Third, in using a non-parametric test, we should really use the real formulas, which can be difficult to compute. So you may need to look it up into a table, or you may need to get my program. But we should use the real formulas, not the asymptotic formulas which are used in some programs. And the fourth of the non-parametric tests, the one that I find the most useful is rank sum. And in doing this rank sum test, in order to get measures of central tendency, a good measure of the difference in central tendency is this z statistic, or the median of the differences between the two groups. That's a useful measure of what the measure of the central tendency is. Okay, so again, I just want to highlight, I mean, I was surprised at the variation. I never understood really, or for a long time didn't understand the difference between the paired and unpaired tests. And I think this really makes that difference really clear. And we really see the difference of that. And also, I think a lot of people are really into whether they got 0.05 or 0.06. And what I'm trying to give you a sense here is that there are a lot of ways in which we handle these statistical tests that can change things. And it's a little bit bad to be too dogmatic about what you're doing about this. And that these tests have assumptions, and if the data doesn't match these assumptions, and again, I picked data here that is particularly non-Gaussian to emphasize the difference. When the data is Gaussian and there are more numbers, then all of these would be, or at least this group and this group together, would be closer to each other. So I've tried to show you, this is kind of not a worst case, but a bad case example. I really want to give you a feel that there's a lot of play in these, and you have to know what you're doing and kind of decide how you want to handle the data, and not go in and use a test and then run 3 more experiments to get it down from 0.07 to 0.05. That there's a lot of give in how we're handling these p-values. Are there any questions about this? All right, I think that's all I wanted to do today. So far we've done parametric tests and now non-parametric tests. Next time we'll go ahead to do the probably most used thing in psychology and statistics, which is analysis of variance. that I have a very low respect for, and we'll do a nova next time. And if anyone hasn't picked up a copy, everyone has a copy of the homework, and everyone has signed the attendance sheet. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay, so I'll see you next week, and you have most of the homework is optional, as you see on homework number 3. So we'll go over that next time. Okay, thank you.